debug formation. Retype it again. So instead of hello world, it's in C. And you say under 50K.
Oh, I haven't seen anyone use VI in about 15 years.
Well, we just did a fresh install, mate. Like, okay.
I use it all the time too. What's that? VI.
Vim. Get with it.
So
Vim.
you said it was going to be 50K?
Or get back to it.
Right. Close. Oh, actually not.
Emacs
50K.
better.
That's still 6K. That's still a lot of stuff. I mean, why is this 6K? We have assembly.
You ever use PostScript?
That's all we have. That's all the code for it.
Really?
Use the libraries that are linked in by
No, I use it.
Our default library
It's a picture.
well, dynamic library.
66 pages.
But we have some sort of stack on stuff. We can get rid of that. That was a bit of code. Stack smash handler. There's a optimization option not to do that, but still quite a bit. So how are programs compiled? And this probably is rudimentary for a lot of you, but we have xload images. Quickly install xload image here. Run this CI. How many people here use Emacs? Okay, do you use Emacs?
I used to. I've been using text editors. I've moved. Well, over the years since graduating undergraduate school, I've moved away from Unix. But the last few years, I've been using Linux, but with a GUI.
Okay, with an editor that comes with it. This is an oversimplified version. We have some source code. We go through a compiler, a linker, preprocessor, a compiler, the new C, and linker, the new linker. Then we have some before we go to the linker, we have some object code. That goes through a linker. We always pretty much get included some static libraries. libc is always static. There's also a library that's pretty much always there, libgcc, for architectures that can't do like 32-bit divides and things like that. So then we have a program binary. And while the program runs, we, of course, have all of this. We have a runtime linker that's encapsulated in the program. We have symbol names and all sorts of information to tell the runtime linker how to put the program together. And we, of course, have an interfacing with the kernel. So, given all that, let's go back to our example. And we can type gcc/verbose to see all the stages of the compiling. This is the compile stage, the preprocessor stage, the compile stage. This is the link assembly stage. Here's where it's linking. It's linking with collect to. You've probably seen some error messages using collect to. But we have a whole lot of crap here. We have some linker arguments, dynamic linker. We have a path to dynamic linker. We have the linking with this library, CRT0, CRT begin, CRT end, and all sorts of other things. Let me disassemble our program, which again is fairly big. we can spell that wrong. Let's see if I spelled it right. Yes. What is?
One F on
Yeah, I would switch that around. So we have a lot of code there. If we can go down to the bottom,
Is the hello world?
this is the hello world.
No.
This is the actual code that we looked at before, where we called printf and also called the stack protector, and this is the actual code that we wrote. And a lot of other code gets stacked onto it. We have the PLT. This is used as a jump reference for dynamic libraries.
What did you use this on? The object?
The binary or
the linked.
Yes, the dynamic linked binary. This is still dynamic linked. We don't have a static binary here, and it still has all this other crap. This is the entry, one of the entry points. This entry point calls constructors, well, ends up calling this entry point, and then this entry point is responsible for building up some of the constructors and deconstructors for doing dynamic symbol lookup and whatnot. And it's a whole lot of crap. So what we can do is we can write a program without any libraries. And unfortunately, to do this, there aren't too many tools to do this sort of thing natively, so we can do it manually. The first thing we can do is we can try and get complete control of our binary. But before we do that, let's describe a little bit what an executable looks like. This is our program as it looks in memory. We have code, data, heap, stack, kernel. The heap is usually maintained by the kernel and gives the code pointers to memory, new memory that it has, or it's maintained by the malloc loop. The standard lib malloc. And then eventually that talks to the kernel and that grows the heap. But then we have stack that's used for procedures that have local variables. Those traditionally are stacked. We have the code that actually consists of the text of the program, what actually gets run. Now, if we take a look at our binary again with object jump, what encapsulates a binary in Unix is called an ELF, an executable loadable format, that's what it's called. And the idea, it's just an encapsulation of different sections. It's an encapsulation of your code section, it's an encapsulation of your data section, and so forth. So let's take a look at our binary real quick, and we see that there are a whole ton of sections. We have a hash section, that's the speed up, lookup. We have the init section where we enter text section, jump table section, read-only data, all sorts of stuff, all sorts of unnecessary stuff. Constructors, deconstructors, the jump pad, and CSS, which is zeros that doesn't get allocated. But taking a look at our diagram from before, these are what some of the sections are. Init, the jump table, text, finalizing is in code. Then for data, we have 3 sections typically allotted for that. We have read-only data, data that gets initialized once but is modifiable. So if you have int b in your global namespace, int x equals 12, x equals 12 will be in data. But you can also say const int x equals 12, and that will be in the read-only data. And then say you have a 0, that will be in this section, which is uninitialized, a reservoir of where 0 data should be.